14-year-old kid from China just sent me his own optimizer. It doesn't perform as well as the best optimizer right now. His is orange, but this is research. This is inventing something and then letting other people improve upon it. Because his optimizer, his idea runs faster with less compute. People complain they don't have 10,000 GPUs, and my bro Xiao here doing all of this research on a CPU. So the blue is the Muon optimizer, the currently best optimizer, and Leo is his optimizer, and I did this ablation. So he sent me the code for the optimizer, and then I programmed it into my LLM, and then I trained it for 10,000 steps to see how it works. I will leave this GitHub repository URL below. You can join my Discord link below, where we do all of this research together, and we can talk about this and do this together. If you don't know where to start or how to go about AI research, or you have some AI research to share with other people, then join our Discord. So Muon optimizer, the best one, is approximating this singular value decomposition that is actually n cube or n cube, a lot of compute. So Muon optimizer actually makes it n squared and 5x because it's 5 iterations for optimal optimizer. And then Leo just grows linearly. So it's Lion with element-wise orthogonalization-proxy. So what I want to stress here is these are the first steps, and this is amazing. So we should not expect somebody to just invent a better optimizer. We need to have a lot of work go into this. But this is really good for understanding why both of these work and how to invent the next one better, faster. I don't know his name, but let's call him Xiao, because that's a Chinese word. So the full singular value decomposition, very expensive to compute. So Muon uses Newton-Schultz approximation. It's like a polynomial, similar to polynomial approximation is how I'm understanding it, but with matrices. And then Xiao invented this. This is his code for linear, less compute intensive approximation of singular value decomposition. Now let's understand Xiao's code. So if we have some update matrix, first we find L2 norms of each row. So the first row norm is 5, and second row 5 as well, so we got 5, 5. Then we take norms of each column, so 3, 0, norm 3, 4, 3, and 0, 4, so 3, 5, 4. Then he is going to divide each row by its norm. So first row by 5 and second row by 5 as well, because it's same. So we get these numbers. So this is the real matrix. Then you see each column, so 3, 5, and 4. Divide each column by its norm, column norm. And now sum the update. So sum this resulting matrix and this resulting matrix to get this update matrix. Now let's calculate this, what's called root mean square magnitude. So basically, we just take this update, we just square each number, and then add. So we square 1.6, it's 2 times, twice, and then 2 zeros and this. So these are the squares calculated here. And then we sum all of those squares and divide by the number of elements, 6. So that's the mean square. And then root of this mean of squares. So that's our RMS magnitude. Before we continue, I want to say the intuition here. So the row term A over the norm, L2 norm of row, makes each row direction unit length. So no row dominates purely by scale. I explained a couple times, so this is a bit tough to explain, but you can have some update weights big, not because they reduce loss, but because they simply multiply big input numbers, for example. So there can be arbitrary reasons why this could be 3000, 4000, 0, and then 0, 3, 4. So if we have this 1000 times bigger row on top, it's not necessarily because that row makes loss, the error of the AI, go down 1000 times stronger than this. It can also be for other factors, other reasons, like exploding vanishing gradients or huge input numbers that are arbitrarily chosen. So I recommend some self-study here, and why we need to normalize update weights, and why do we normalize numbers in neural networks. Then we do same across the column. Adding them encourages balanced contributions across both row and column directions. It's not true orthogonalization, but it often reduces harmful alignments and stabilizes update. Final RMS scaling guarantees a controlled step size regardless of the raw magnitude. This is what I was explaining. So to finish the final step, we pick some, so there is some align constant. I'm not exactly sure why we need this, but we divide that align constant with our RMS magnitude, and then multiply entire matrix with this RMS magnitude. So I guess that's just scaling, normalizing also. We got some tips. We have minimum value. If it turns out that row norm is 0, we actually don't want to be dividing with 0, so we have like some minimum value that's close to 0 but not 0. Then I did some other experiment. This is the whole explanation here as well. I did some search for learning rate. If you notice, my learning rate is very low here. Look how much lower it is than Muon. I just found out that it works best this way. I'm not sure why exactly. Maybe if also we find out why learning rate needs to be so low, then we can fix that error and maybe this would converge faster. Because the whole point here is that we have linear compute as opposed to quadratic compute. Also, I didn't measure memory. Does this take like less memory? Because Xiao said he just had like a CPU. I told him to use these free GPUs like Google Kaggle, Baidu AI Studio and stuff. Imagine doing AI research on CPU, bro. How much time do you need? Like 20 times more time. I can't get over it. He was training it on a CPU, bro. Why are we complaining we don't have like 10k GPUs? We don't have 100,000 GPUs. Here I found the trend that lower learning rate for Leo works better. That's why I just tried a bunch of learning rates and found this one to work best. I don't know why though. Maybe this is a topic for future research. Join our Discord community where you can talk to Xiao and mathematicians, researchers, and everything. We got a bunch of stuff here. So we are building this Blueberry LLM. Blueberry is gonna be name of our community, and we're gonna make other models like Blueberry image, Blueberry video, or something like that. We'll see. So on Discord, if you scroll down, you can see all of the courses I have. We can learn AI, have learning AI research. We also have our projects that you can work. So I'm making these like tickets. You can pick these tickets and or create new tickets and do some research. You can create your own projects if you have some research, or if you are a PhD student or assistant or professor, or we invite you to show us or to publish your research here. We're gonna help you. And for anybody else who is working on research, you're all invited and we can do this research here. I plan for this to be like a online global open source research kinda institute or a startup, but without money. We don't have any money here. We are just like doing like using free Google Colab or renting some cheap hardware and doing the research. And we're gonna compete with everybody. I imagine this as like publishing papers every day. I get a lot of people here. We all work together. We publish like so many quality papers from all around the world. You don't need to get some unobtainable degree or some position that you need like 20 years of experience. You can start doing research right now. So join the Discord and see you in here.